Okay, so today's plan is that I'm going to finish the introduction to stellar astrophysics. So I will reserve maximum 1 hour for this, and for the rest of the time I will show and explain you how you can use the AstroHub TINA computational tools. Okay, so by now most of you already sent me your GitHub IDs, and those who sent the GitHub IDs now should have an access to both TINA and public and outreach AstroHub servers. I will show you after I will finish the introduction to astrophysics how to use those tools. Okay, so now let me go to the introduction to stellar astrophysics where we stopped last time. Okay. So can you see my screen? Anyone?
Not yet.
Yeah, not yet.
Do you see it?
There is no screen sharing right now.
Oh, sorry. Yeah, I forgot to share my screen. Thank you. Yeah, you see, I have just a second. Yeah, that's correct. I forgot to share my screen. Okay, I go here. Here, share. Sorry. Participant can now see your screen. Okay. So now I go back here, full screen. I think I should leave just. Okay. So now you can see my screen, right?
Thanks. Yeah, now we can see your screen, but there is a chat when. Oh, yeah, perfect. We can see your screen.
It's okay?
Yeah. It's
okay.
Perfect.
Thank you. Okay. So now last time we stopped here. So this is just a definition of a star. Okay. So this is not an official definition. Yeah, Nikhil. Yeah. What's the question?
I'm sorry. Before we start, so I think you told us like you're gonna upload the session that we had the last time on somewhere.
Yes, I sent a link to the video recording. You didn't get it, Nikhil?
No. Oh, did you send it on an email or like did you post it in the same channel?
I think I sent it via email.
Oh, I'm not sure. I don't think so. I got it.
Okay, so after today's lecture, I will send the link to this new video and to the previous one. Okay, and make sure that everyone will get it. Okay.
Okay.
Yeah, it's on YouTube, but only those who get the link can access it. So therefore, you are supposed to get the link. I will send it. Okay. But I saw in email that at least some students got the link and tried to watch the video. Okay. So now, yeah, this is the link. Yeah, thank you. Okay. So now let's go back to the introduction to stellar astrophysics. So this is a definition of a star. It's not an official, but I think it's correct. So let me just read it. And yeah, a star is a gravitationally bound, spatially isolated mass of baryonic matter that is opaque for radiation, in which thermonuclear reactions transforming hydrogen into helium had either occurred in the past, occurring at present, or will occur in the future on a relatively large scale. So I think that everything what is important for the definition of a star is included in this sentence. If you will find anything missing in this definition, just please send me by email your thought. Okay. So now next slide. Okay, next slide. So this slides just lists the fields of physics that benefit or are used by the physics of stellar evolution and stellar structure. So physics of stellar interiors benefits from the following fields of physics. From classical mechanics, and I hope that you are familiar with the virial theorem, because from my point of view, the virial theorem is important, very important for stellar physics, because what it actually tells us is that when a star loses a state of thermonuclear thermonuclear equilibrium, it begins to contract by gravitational force, and as a result of this gravitational contraction, the star actually heats up. Temperature inside the star increases, which can lead to ignition of the following thermonuclear fuel. So therefore, I think the virial theorem is very important for stellar physics. Of course, the stellar evolution and stellar physics benefits from hydrodynamics, because convection and other mixing mechanisms are important for both the evolution of stars and also for studying nucleosynthesis stars, production of chemical elements and isotopes, because nuclear reactions change chemical composition inside the stars, but also mixing changes chemical composition, right? So therefore, hydrodynamics is important. Radiative transfer theory, okay, describes how heat is transported inside the stars, where there is no convection, where there is radiative transfer. Okay. Thermodynamics and statistical mechanics. For instance, radiation transfer is switched to electron conduction in the white dwarfs, and of course thermodynamics is also important for, say, calculating the term that describes the production of gravitational energy. I will show this in a minute. Atomic and molecular physics, obviously. Nuclear physics, of course, most of you are nuclear physicists. Quantum mechanics, I will show in one of the next slides that the tunneling, the quantum mechanics tunneling effects is, of course, very important for nuclear physics, as most of you already know. General relativity for compact objects like even white dwarfs, but of course neutron stars and black holes. Electromagnetism, that there is quite a lot of magnetic activity in solar type stars, including the sun. And solid state physics, this is important for very dense objects like cold white dwarfs, where material forms actually lattice. So therefore solid state physics is important there. And of course, the physics of stellar interiors deals with material in conditions that are not attainable in laboratory experiments on Earth. So therefore, it's very important to study it. Okay. So now, this slide shows a system of 4 partial differential equations. Okay, that describe stellar structure and evolution. PDEs that describe stellar structure and evolution. So the first equation is the equation of hydrostatic equilibrium. The gradient of pressure is equal to minus with minus sign density, mass density multiplied by the gravitational acceleration g. Okay, and this is expression for the gravitational acceleration. Gravitational acceleration at the surface of a sphere with enclosed mass m sub r and with radius small r. So of course, it's important to note that these equations described a spherically symmetric star, which means that they describe structure of the star and its evolution only in one dimension. So therefore, as an independent variable in this one dimension, we can choose either radius small r or the enclosed mass capital M sub r, which is a mass inside a sphere of radius r. And most stellar evolution codes, including MESA, they solve the equations of stellar structure and evolution in 1D, in one dimension, of course. So the second equation after the equation of hydrostatic equilibrium is just the mass conservation equation. It just relates the radius of a sphere of the radius small r with the enclosed mass inside the sphere. It says just the partial derivative of mass with respect to radius, of course, 4 pi r squared rho. Or this also, if we integrate it, it just connects, relates the mass inside the sphere of radius r with the radius. So the mass sub r will be integral of this expression from radius 0 to given radius r. The third equation describes how heat is transferred inside the star from its center to the surface. Of course, the center has the maximum temperature, usually in most cases has the higher temperature, surface has much lower temperature, and therefore there is a temperature gradient. So here the temperature gradient is either the derivative of temperature with respect to radius, this one, or this nabla. I will show the expression for nabla later. Nabla is also called temperature gradient, but it's a logarithmic and with respect to pressure. And this is just an identity, as you can see, which defines nabla via the ordinary radial temperature gradient. So the physics for this equation, for the heat transfer inside the star, the physics for this equation is actually included in the right expression for this nabla, logarithmic temperature gradient with respect to pressure, about which I will talk in the next slide. Finally, the last and the fourth and the last equation, 1, 2, 3, 4, is the energy conservation equation. Okay, so all these equations actually come from the conservation equation. The first one is the momentum conservation. The second one is mass conservation. The third one just the thermodynamic condition for temperature gradient. So heat flows from hotter regions to colder regions. And the fourth equation is energy conservation equation. It just also relates the gradient of luminosity, and this capital sub r is the luminosity of a sphere of radius r, like the mass enclosed in the sphere of radius r. This is luminosity at the surface of the sphere of radius small r, and luminosity is defined as the total energy emitted from the entire sphere per 1 second. So therefore its units are, say, joules per second, or in astronomy we use centimeter gram per second units, so therefore its units are erg per second. And this is also just an identity which transfers the radial temperature gradient to its mass gradient via the derivative dmr over dr. And what's important, again, like for nabla, for temperature, what's important here is the expression for, okay, this is probably, I think, this is probably someone external, okay. Okay, the physics is included in this derivative of luminosity with respect to mass coordinate, for which the expression is given here. So as you can see, this is actually the luminosity of the sphere of radius r calculated per unit mass of the same sphere, and it's equal to the sum of these three terms. Each of these terms, of course, has units erg per second per gram. Okay, and these three quantities define the so-called energy generation rate. So epsilon sub n is the nuclear or thermonuclear energy generation rate, therefore n stands here for nuclear. The epsilon sub g, g stands for gravitational. This is the gravitational energy generation rate. And with minus sign comes epsilon sub nu. This is usually energy loss rate associated with emission of neutrinos, because in most cases, except the co-collapse supernova, neutrinos escape from the star, leave the star without interacting with baryonic material. So, and usually this is energy loss. So therefore this term, which is here positive, comes with minus sign, meaning the energy is lost. So in this, for equations of stellar structure and evolution, capital P is pressure, R is the distance from the center to the surface of the sphere of mass m sub r, luminosity L sub and luminosity L, capital L sub r. Rho is the mass density. G here is the Newton's gravitational constant. Small g, as I already explained, the gravitational acceleration. These are the rates per unit mass of energy generation loss due to nuclear reactions, etc., etc. Okay, let's go to the next slide. So the next slide, as I promised, explains the meaning of the nabla, of the temperature gradient nabla. So the temperature gradient dTdr depends on how fast heat is transported by radiation and convection, right, which is determined by this nabla. There are two main ways how heat can be transported inside the stars. The first one is convective heat, like in a boiling kettle, water in a boiling kettle. And the second is radiative heat transport, like in a room, heat is transported if there is no convection. Solar heat is transported to us by radiation. So if convection is efficient, in other words, non-leaky, which means that when convective element, a convective fluid element is transported readily, it doesn't lose heat from its surface. For this, of course, material should be radiatively opaque, and this is true for deep interiors of the star, except subsurface layers of the star. So for an efficient non-leaky convective heat transport deep inside the star, the temperature gradient, of course, is equal to its adiabatic value, adiabatic temperature gradient, which can be calculated, this quantity, from thermodynamics, okay? It's adiabatic because, as I said, in this case, we can assume that fluid elements, convective fluid elements, doesn't lose its heat, which means adiabatic changes. If we don't have convection, then heat is transported by radiation. In this case, this nabla, logarithmic temperature gradient with respect to pressure. By the way, this is a typo. This should be d logarithm temperature divided by d logarithm pressure. I will correct this. So this is the reverse thing. So for radiative heat transport, nabla is equal, it's called nabla sub red for radiative, and it's equal this expression. In this expression, this small a is the radiation constant, the physical constant, and kappa is the Rosseland mean opacity of stellar material. So kappa is the opacity coefficient, which describes how opaque stellar material is. So there are tables for kappa as a function of density, temperature, and chemical composition. So these tables are usually used by stellar evolution codes, for example, by MESA. So everything else is familiar for you here. See the speed of light in a vacuum, luminosity, mass enclosed, P pressure, T temperature, okay? So now the gravitational energy rate, which is included in the previous equation, epsilon sub g, can be calculated using, again, thermodynamic equations. So by definition, this is minus dq dt, where is q that is that we supply fluid element with q heat, okay, and the rate with which the fluid element releases the heat, therefore it comes with minus sign, is included in the gravitational energy source. And according to thermodynamic equations, this is minus the rate of change of internal energy, capital U is internal energy, per unit mass of the fluid, plus this mechanical term, which is known from thermodynamics as PDV. But dV, V here, V is specific volume, volume per unit mass, which is replaced by density here, okay? And using thermodynamics, we can transform this expression to this expression in which capital C sub P is the specific per unit mass heat at constant pressure, and nabla ad is this just adiabatic temperature gradient. Again, this is logarithm temperature over logarithm pressure. This is just typo, okay? Finally, this quantities that enter all these equations: pressure, internal energy, specific heat per unit mass at constant pressure, adiabatic temperature gradient, opacity kappa, nuclear energy rate, generation rate, neutrino energy rate. All these quantities are provided as functions of temperature, density, and chemical composition. Now you know capital X mass fraction of hydrogen, capital Y mass fraction of helium-4, and Z mass fraction of heavy elements besides hydrogen and helium. So Z is equal 1 minus X minus Y. So all these quantities are usually provided as functions of temperature, density, and chemical composition by the so-called input physics data, which in most cases come in the form of tables that are used by stellar evolution codes, in which the stellar evolution code just interpolates in temperature, density, and chemical composition. Okay, so now I provide a few slides that illustrate what I've just said. Heat transfer in stars. So these are main sequence stars that burn hydrogen in their cores in the centers, including the sun. Depending on the initial mass of a main sequence star, there can be the different parts of the star have different heat transfer mechanisms. For instance, if you take a very low mass star, a main sequence star with mass smaller than half solar mass, in this case, in almost the entire star, the heat is transported by convection, which means that all low mass main sequence stars are fully convective. They are fully convective. Heat is transported by convection. Okay, so convection here is shown by these loops. Okay, because convection usually makes a complete mixing of the star. If we take a star with a mass close to the solar mass, between half and 1.5 solar mass, say around 1 solar mass, then the core of the star, in the core of the star, heat is transported by radiation, which is shown by these arrows. The white part, core is transported by radiation, while in the envelope close to the surface, heat is transported by convection. So such solar type stars have a radiative core surrounded by convective envelope. And finally, when we go to more massive main sequence stars with masses say above approximately 1.5 solar mass, then it's a reverse situation compared to solar type stars. In these stars, in massive main sequence stars, we have a convective core at the center. So heat is transported by convection in the core, while the envelope, in the envelope, heat is transported by radiation. So this situation is reverse compared to solar type stars. Okay. So now, of course, the question is, when you look at the equations of stellar structure and evolution, then you don't understand why stars evolve, why their structure changes with time. But obviously, the structure of stars changes with time because in order to support their luminosity, they have to have an energy source. And this energy source can either be gravitational for a relatively short time or for longer times. This energy source is provided by thermonuclear reactions. And thermonuclear reactions, they change chemical composition inside the stars, right? And changing chemical composition is actually what drives the evolution, what drives the change with time their structure. And this equation they summarize in a schematic form how thermonuclear reactions change chemical composition inside the stars. So therefore, they called the equations of the kinetics of stellar nucleosynthesis. And these equations are important for us, for you and for me, because we are going to study nuclear astrophysics, assuming that stellar structure and its evolution, its change with time, are provided by stellar evolution code. In our case, this in most cases will be mesostellar evolution code. Okay, so we are not going to care much about stellar structure and evolution. Instead, we are going to care more about the change of chemical composition in stars, okay, as a function of time, and therefore we are interested more in equations of kinetic of stellar nucleosynthesis. Okay, and this slide summarizes schematically these equations. So let's say we have the ice and trace isotopes that fuse together, right? So this can be, for instance, hydrogen, protons, and carbon-12. Okay, therefore, for the reaction carbon-12 p gamma, right? So when the ice and trace isotopes fuse in a star, and as a result, this produces the case isotope. Okay, carbon-12 p gamma makes nitrogen-14, for instance. In this case, ice isotope is carbon-12, trace isotope is proton, hydrogen-1, and case isotope is nitrogen-13. Okay, and let's also assume that the freshly produced case isotope, in my example, it's nitrogen-13, is unstable. Indeed, nitrogen-13 is unstable with a half-life, with a lifetime about 10 minutes. And if case isotope is unstable with an exponential lifetime tau sub k, then its number density, the number density of case isotope in these reactions, in these two reactions, its production and its decay, its number density can be determined as a solution of the following differential equation. So this is the ordinary differential equation. The rate of change of the number density of the case isotope is equal to this expression. So here, the first term takes into account the production of case isotope from the ice and trace isotope. These are number densities of the ice and trace isotope, and this term takes into account decay of the case isotope over the exponential lifetime tau k, right? So in this equation on the right hand side, this sigma sub I comma j is a cross section of the reaction between the ice and trace isotope. V is the relative velocity, and angles here mean averaging over the Maxwellian distribution of the relative velocity V. Okay, so the kinetic equation, this kinetic equation can also be written in the following form. This is what's usually done by nuclear astrophysicists. So we switch from number densities N here to the so-called molar densities Y. Okay, but this is the same equation, but we switched from number densities N to molar densities Y, where the molar density of the ice isotope here is defined as its number density divided by mass density rho and divided by Avogadro's number, which turns out to be, as you can see from the previous slide, is the mass fraction of the ice isotope divided by its atomic mass. Okay, and Avogadro's number, of course, a reverse of the atomic mass unit. Okay, and in this equation, in this form, this lambda sub I comma j, this lambda sub I comma j is the product of excuse me, is the product of Maxwellian average cross section of the corresponding reaction and multiplied by Avogadro number. And this is lambda. This is what is usually called a reaction rate. This is the standard expression for reaction rate. And this lambda, this product, is usually what you can take from tables of reaction rates. Okay, this is what's usually provided in the literature, for instance, in the Gino reactive of reaction rates. So I spent quite a few time explaining you these equations because this will be the focus of our studies, of our research projects, nuclear synthesis and stars, right? Okay. Okay, so now this should be familiar for most of you. This is just a fragment of the so-called the chart of nuclides, right? And usually horizontally from left to right, we plot neutron number. So neutron number increases from left to right, and vertically we usually plot the proton number or the charge of isotope, and the proton number increases from bottom to top. Okay, so therefore, when we go diagonally from bottom left corner to the top right corner, this means both neutron number and proton number both increase, which means that atomic number, which is sum of neutron and proton number, also increases. As you can see, atomic number is shown here like 26, 25. This is atomic number. So now dark blue boxes are stable isotopes. For instance, nitrogen 14, nitrogen 15, magnesium 24, 25, 26. So dark blue are stable isotopes. Everything else are unstable isotopes. And the region of occupied by this dark blue boxes is called the valley of stability, because this is a region of stable isotopes. When we go away from the valley of stability in either direction, to the right or to the left, we leave the valley of stabilities and we find ourselves in the region of unstable isotopes. And the further away we go from the valley of stabilities, the shorter are lifetimes of the corresponding isotopes. And their lifetimes are shown here with colors. As you can see, the half-life of the corresponding isotopes is shown for this color, the closest to the value of stability in years. Then half-life with this color is shown in months, then in days, hours, seconds, milliseconds, microseconds, and so on. Finally, when we approach here to the right, the so-called the neutron drip line, isotopes that cannot hold any more neutrons. Here you can see the lifetime is in nanoseconds, and there are no. So yeah, when we go to the left from the valley of when we go to the right from the valley of stability, this means we move towards neutron-rich isotopes. Okay, when we move to the left from the valley of stabilities, we moving in the region of proton-rich isotopes. And of course, science, nuclear astrophysics should explain the origin of all isotopes, including proton-rich and neutron-rich, okay? If there are stable isotopes that are proton-rich and neutron-rich, okay? So as nuclear astrophysicists and as nuclear astrophysicists who collaborate with nuclear astrophysicists, we will be having a lot of looks on chart of nuclides, like the fragment shown here, right? Okay. Okay. So now most of you probably know that when we plot the nuclear binding energy per nucleon vertically here as a function of mass number, there is a prominent peak on this curve in the region of iron. Therefore, this peak here of this curve is called the iron peak, which means that the nuclear binding energy per nucleon decreases when we go from iron peak in both directions, to the right and to the left. This means that we can produce elements by fusion up to the iron peak with a release of positive energy. Okay, so fusion, thermonuclear fusion reactions can provide stars with energy only until we reach the production of iron. So therefore, as you know, the latest thermonuclear burning phase in massive stars is silicon burning, which makes iron peak nuclei here. After that, the star cannot release energy from fusion reactions, and the iron core is the final stage of the evolution of massive stars. After that, iron core experiences collapse, and as a result, we have a co-collapse supernova explosion, leading to the production of either neutron star or a black hole. Okay, so therefore, only reactions that include isotopes and nuclei lighter than iron, their fusion can produce some energy. So therefore, we start, by the way, from deuterium burning, H2 burning, still on the pre-main sequence evolutionary phase during gravitational contraction of stars before they have reached the main sequence, hydrogen, the co-hydrogen burning phase. Then on the main sequence, we have hydrogen burning, which makes helium-4. And a lot of the most energy, as you can see, is released during hydrogen burning, which makes helium-4 almost the entire energy of binding energy can be released during hydrogen burning. So after that, we have helium burning, which makes carbon-12. You can see much less energy, relative amount of energy is produced during helium burning. Then we have carbon burning, neon burning, oxygen burning, silicon burning, and that's it. These are all fusion reactions that can release energy and supply stars with energy to compensate their luminosities, right? Then the question, of course, arises how elements, isotopes that are heavier than iron peak elements can be produced. They cannot be produced in fusion, okay? So for the production of elements heavier than iron, we can use neutrons because the capture of neutrons, when we have reactions with neutron capture, they don't have to penetrate strong Coulomb barrier because neutrons don't have electric charge, okay? So therefore, the production of elements heavier than iron occurs in neutron capture processes. There are a few neutron capture processes about which I will talk later, okay? So this proton-proton chains of reactions which are active, predominate in relatively low mass stars and solar type stars and in low mass main sequence stars during hydrogen burning. So I'm going to go faster through the slides because you can have a more detailed look on the slides later, because you can download, clone them, right? So proton-proton chains. In proton-proton change, interesting neutrinos are produced. For instance, boron neutrino, as well as other neutrinos. And most of these neutrinos have already been observed, have already been detected. And their detection confirmed our right presentations about hydrogen burning in stars, and both actually in proton chains as well as in the CNO cycle. This diagram shows hydrogen burning in the so-called CNO cycles. I already mentioned this reaction, carbon-12 p gamma nitrogen 13. Then proton captures the nitrogen 13 experiences positron decay, making carbon-13, then next proton capture, and so on. And this is the first cycle, cycle 1, which is often called just CN cycle, because it doesn't include stable oxygen isotopes, only unstable oxygen 15. This first cycle is closed when nitrogen 15 captures proton and releases alpha particle, making again carbon 12. So this is the cycle. So this is the second cycle, which involves stable oxygen 16 nuclei, and this is the third cycle. There is also fourth cycle. So you can have a look at this cycle in detail later. Besides CNO cycles in massive main sequence stars, some reactions of the so-called neon sodium magnesium cycles can also be active. For instance, in massive main sequence stars, this reaction is active, neon 22 p gamma sodium 23, which consumes initially more abundant neon 22 and makes sodium 23. This reaction can go even on the main sequence because it's a resonant reaction. I'll explain you this later, but most of you, some of you know what resonant reaction actually means. And also some reactions of magnesium aluminum cycles, for instance, magnesium 25 p gamma, can go on massive stars and some other reactions. But this doesn't mean that entire neon sodium magnesium aluminum cycles operate in massive main sequence stars. They can operate in later evolutionary phases when temperature becomes much higher. Okay. So this slide just explains the importance of quantum tunneling through Coulomb barrier for charged particle thermonuclear reactions in stars. I'm not going to spend much time on these slides because this is a well-known physics, should be known for you. So there is a Coulomb barrier when we consider thermonuclear reaction between electrically charged particles. So for instance, again, proton and carbon 12, they are both positively electrically charged, and there is Coulomb barrier. And it turns out that even the temperature, which is inside the stars, is not sufficient for electrically charged particles to directly form a compound nuclei. They still have to go below the Coulomb barrier. And for this, of course, particles use the quantum effect called quantum tunneling. So this slides mention this. The second effect that strongly reduces reactions is actually angular momentum. The second effect is the angular momentum conservation. So it's easier, so we have to, so particles have to obey the angular momentum conservation. So there are two effects that actually hinder reactions, Coulomb barrier, and the second is angular momentum conservation, okay? So as I already mentioned, so this curve on the left, it shows Maxwell-Boltzmann distribution of energy of charged particles inside the star, okay? And this curve shows the probability of electrically charged particles going through a Coulomb barrier via this quantum tunneling, okay? So the probability, of course, of quantum tunneling increases with energy, but there are not too many particles at this energy, according to the energy distribution for stellar temperatures. So therefore, it turns out that thermonuclear reactions in stars go between particles which have energies in between here, in between these two curves. And the resulting curve, which is just the product of these two curves, is called the gamma curve. And where it has peak at energy, which is called gamma peak energy, this is the energy of particles, electrically charged particles, that are responsible for thermonuclear reactions in stars at gamma peak energy, but most of you probably familiar with this. Okay, as I already mentioned, some thermonuclear reactions go through the so-called resonance states. This means, for instance, this reaction, which is beryllium 7 p gamma boron 8, you can see its cross section has a very sharp peak at a certain energy, and this peak corresponds to the resonant energy state inside the compound nuclei produced by beryllium-7 and proton. As you know, like atoms, nuclei have quantum states, and when the energy of interacting particles, the sum energy happens to be close to one of these internal nuclear states of compound nuclei, then the probability of such a reaction at this energy increases considerably. And I already mentioned, for instance, neon 22p gamma reaction, which makes sodium, turned out it was clear in 1980s. It turned out to have a low energy resonance, which is responsible for this reaction neon 22p gamma, not this reaction, going relatively fast even in main sequence, massive main sequence stars. So therefore, it's important to remember that there are the so-called resonances in reaction rates, like this resonance shown here for this reaction beryllium-7p gamma. Okay. So now, when we plot the ReLF energy generation rate in pp chains, the blue curve, and then the CNO cycle, the red curve, as a function of temperature, say co-temperature means temperature at the center of the star, right? Then we see that the energy generation rate in the CNO cycle during hydrogen burning in main sequence stars, it becomes higher than the energy generation rate in p chains, approximately at temperature around 17-18 million Kelvin. And the sun, the star, the closest to the Earth, the sun, of course, it has at the center temperature around 15 million Kelvin. And as you can see, this temperature, the energy production in pp chains dominates over the energy production in the CNO cycle, right? So therefore, in the sun and the solar type stars, as well as in main sequence stars with mass smaller than the solar mass, the hydrogen burning occurs predominantly via pp chains, as you can see. While when we go to more massive main sequence stars with central temperature above around 17-18 million, which corresponds to initial mass above around 1.2, 1.3 solar masses, the energy production in the CNO cycle becomes dominating. So, and therefore in these stars, excuse me, in these stars, hydrogen burning occurs predominantly via the CNO cycle. And it is because the energy production in the CNO cycle is much more stronger temperature sensitive. Epsilon production in the CNO cycle is proportional to temperature to the power 17, while in the pp chains to the temperature to the power 4. Such a strong dependence of energy production on temperature is actually responsible for the presence of hydrogen convective cores in main sequence stars more massive than approximately 1.3 solar masses. Okay, so this is how nuclear physics explains the differences in the structure of stars. In this case, main sequence hydrogen burning stars. Okay, so after hydrogen burning, when hydrogen is exhausted and stars have helium cores, so after hydrogen burning, thermonuclear fusion in stars switches to helium burning, helium fusion. And helium fusion occurs in stars via the triple alpha process or triple alpha reaction. So for this, we need actually to make one carbon-12 nuclei, we need 3 alpha particles. Therefore, it's called triple alpha process. So first, fusion of 2 alpha particles makes 1 beryllium-8 nuclei, which is unstable with a very short lifetime. So it decays back into 2 alpha particles. And when during its short lifetime, the third alpha particle approaches to beryllium-7, then this makes carbon-12. Okay. And again, you know that for life we need carbon. For life we need carbon, and if this reaction was not a resonant reaction, stars couldn't produce carbon, and there will be no life. So it is thanks to resonance in this reaction that stars are capable of producing enough carbon in their course to eventually make life. So this is an important reaction as well. Okay, so this is a movie animation that shows the evolution of one solar mass star. I'm not going to show this movie right now. You can press this button in your slides later and have a look at this movie, okay? Because I want to go, I want still to explain you how to use the TINA AstroHub server, and the time for the introduction to stellar evolution that I reserved is almost up. There are only 5-6 minutes left, so I'm going to skip this movie. Okay, so this slide, let me check how many slides I still have. 1, 2, 3, 4. That's it actually. Okay, so I have time to finish my slides. Okay, so this slides shows the main evolutionary phase, the main evolutionary phase in the evolution of solar mass star as well as intermediate mass star with initial mass 5 solar mass. So as you can see, this is a theoretical Hertzsprung-Russell diagram, because we plot here luminosity as a function of effective temperature, surface temperature of the star. Okay, so because we are going to study nuclear astrophysics, and stellar astrophysics is important for this, I have to be sure that we understand each other. We understand, for instance, the major evolutionary phases of stars. When we take one solar mass star, like solar type stars, the pre-main sequence evolution is not shown here before the main sequence. This is the phase when the star contracts towards the main sequence and temperature at the center is not high enough to ignite hydrogen. But when the star arrives on the main sequence and temperature at the center is sufficient to ignite hydrogen, this is called the 0H main sequence. And this is the this point, 0H main sequence. When a star burns hydrogen in its core, this corresponds to main sequence evolutionary phase. And it's not just one point. This is this segment of the evolutionary track, this evolutionary track. Then at this point, when the star reaches the maximum effective temperature, remember effective temperature increases from right to the left, hydrogen is exhausted in the core and the helium core is formed, and hydrogen burning switches from the center to the shell around helium core, and the star leaves the main sequence along the subgiant branch. Then it arrives at the bottom of the red giant branch. So this is the red giant branch, okay, which is not indicated here. This is the red giant branch. Then the star burns hydrogen in a hydrogen burning shell atop of a helium core, inert helium core. And as a result, it moves along the red giant branch. It climbs the red giant branch. At the tip of the red giant branch, the temperature in the helium core reaches high enough values of water, 100 million Kelvin, so that helium is ignited. In low mass stars, the ignition of helium is violent. It's called the helium core flash. You can see the helium core flash on the movie that I skipped. And after the helium ignition, the low mass star arrives on the horizontal branch. So this is ZAP, is the 0H horizontal branch. On the horizontal branch, low mass stars burn helium in their convective helium cores, convective helium cores. After helium is exhausted, we have carbon-oxygen core formed at the center, which is actually a carbon-oxygen white dwarf. And burning is switched to hydrogen shell and helium shell burning. You can see this on the movie that I skipped. and the star arrives on the asymptotic giant branch. On the asymptotic giant branch, the structure of the star is carbon-oxygen core at the center, surrounded by helium shell and hydrogen shell. And hydrogen and helium shell burning, they occur intermittently. So first hydrogen burning, then helium shell burning, and etc. And the star experiences so-called helium shell flashes when helium shell is ignited. And eventually it arrives to the tip of the asymptotic giant branch, where it loses its entire hydrogen-rich envelope in the event called mass loss. But in this case, at the tip of the AGB, the mass loss has a very high rate, and the entire hydrogen envelope is lost, and the carbon-oxygen white dwarf, which is a remnant of the evolution of low mass stars, moves horizontally here and begins to cool down. Then it can the helium shell, which is left atop of the carbon-oxygen core, can experience the last helium shell flash, and the star makes this loop, and eventually the carbon-oxygen white dwarf cools down. This is the so-called white dwarf cooling sequence. The similar evolutionary sequences occur only for the intermediate mass stars, 5 solar mass star, 0H main sequence turnoff, subgiant branch, red giant branch, helium burning. During helium burning, convective helium burning, it makes a loop, which is similar to horizontal branch. Then it finds itself on the asymptotic giant branch. Mass loss, and the core, which is more massive for more massive initially stars, carbon-oxygen core cools down, becomes white dwarfs. Okay, excuse me. Okay, so this slide summarizes what I've just said. The final products of the evolution of stars with different initial masses. You can have a look at this slide and read the caption, but it actually summarizes what I've just said. Okay. The major evolutionary phases of low intermediate mass stars. Okay, so now this is about the evolution of intermediate mass stars on the asymptotic giant branch, low and intermediate mass stars. As I mentioned, they experience from time to time thermal pulses of helium shell. This is shown here. As a result of helium shell, the pulse-driven convective zone develops. So this is PDCZ, stands for pulse helium shell pulse-driven convective zone. Okay. So immediately after the pulse-driven convective zone, the base of the convective envelope penetrates the previous location of the helium shell, dredges up some products of helium to the surface by convection. Okay, and also ingests some hydrogen below. We don't know exactly the physical mechanism of this hydrogen ingestion, but it should be there. And the ingested hydrogen later, between successive thermal pulses, this hydrogen is captured by carbon-12, which is abundant here, which makes carbon-13, and carbon-13 captures alpha particles, which releases neutrons. And these neutrons are captured by heavy isotopes in this region, which makes heavy elements beyond iron. And this is what's called S process, or slow process of neutron capture. So you can have a look at these slides later. We can talk about this later. Now the final plot here summarizes actually different processes that can occur on the chart of nuclides. Okay, so I already mentioned S process, slow process of neutron capture. So when stable nuclei capture neutrons, and when this neutron capture process reaches the first unstable nuclei, it experiences beta decay, okay, to the next stable nuclei, then neutron capture to the next unstable nuclei, again, beta decays to stable nucleus. This is the path of the so-called slow process of neutron capture, okay? S process occurs when neutron density is relatively low. 10 to the 7, up 10 to the 10 neutrons per cubic centimeter. So therefore, neutron density is not high enough for unstable nuclei to experience further neutron capture. So therefore, S process goes along the right boundary of the value of stability. But if neutron density is much higher, or for the 10 to the 20 neutrons per cubic centimeter, then even this unstable nuclei can still capture neutrons because of high concentration of neutrons. And this neutron capture process can reach the neutron drip line. And this is how our process, rapid process of neutron capture goes. It goes close to the neutron drip line. And of course, now we know that there is an intermediate process of neutron capture for neutron density between those characteristics for S process and R process, which means for neutron density is around 10 to the 13, 10 to the 15. And I process, this intermediate process of neutron capture, which we call I process, allows us to reach neutron unstable nuclei in between the value of stability and the drip line. So it goes, its path goes here in between S process and R process. So this is the last slide that I wanted to show you. Okay, and now I'm going to switch to explain for you how to use TINA computational tools. Okay, so I'm going to go to here's empty screen, and as the instructions for CaNPAN project tools explain you, we recommend to use Google Chrome browser. Okay, so I have opened Chrome browser. Then you go to AstroHub server, astrohub.uvic.ca. You know this, right? Okay, and you will find yourself here, right? As I already said before, without being a NuGrid member, so this red square is for NuGrid members only, but in principle you can become a NuGrid member. I explained how to do this. So, but if you are not a NuGrid member yet, you can still use these two servers. So I will talk about how to use public and outreach server next time. But now I'm going to focus on how to use this server, TINA. It's called TINA. TINA stands for Training in Nuclear Astrophysics. So when you are here, you click on this orange square, TINA. Then you will see something like this. Or maybe you will be asked to provide your Git password. I don't remember. But eventually you will find yourself here. Application Network Simulator. You spawn it, so you click this orange bar, okay, and you wait less than a minute. Then you will find yourself here. So this is a, yeah, this is the, you are in the hub, TINA hub, okay, and here, the first thing you, of course, see on the left, in the left margin, there is a README file. To open this README file for it, you click right button and you go to open with Markdown preview, not with editor, but Markdown preview. When you click this README file, as explained, right button, open with Markdown preview, you will see this short README file, which explains what you can do with TINA. So what it actually tells you so it's actually, sorry, not what you can do with TINA. It explains you how you can start using TINA. Okay, how you can start using TINA. Okay, so actually it says that for you to start using TINA, you should go to network school and use the notebook make new iProcess user directory, this notebook. Okay, so this means you go to network school here. Oh, Just a second. No, I'm okay. Just to get started directly in the user. Yeah. Yeah. So you go here, and there is here the notebook. Oh, no, this is not. What is it? What is it?
Prof, I'm having an issue
Yeah.
because when I sign in with my GitHub to enter into the Jupyter notebook, it displays an error saying error 403 forbidden. So I don't know what is happening.
No, error 403 means that you are not Guillermo. Just a second. Guillermo, you haven't sent me your GitHub ID yet, right?
That is true. I'm sorry. I did not.
Yeah. Because you should send me your GitHub ID so that we can add it to the access list. Okay.
Perfect. Thank you.
Yeah, but I don't understand. To get started, select the directory networks in the file manager. If you are a new user, create a new person using my. Where is this make new iProcess notebook? I mean, I have already my directory here. Yeah, it's probably because I already have a directory, right? Okay. So it says when you a new user, I'm not a new user, you will see this notebook, make new iProcess user directory. Tell me if you don't see it, okay? Because then you go to this notebook and provide a name for your directory, okay, to create. And I already have this directory created, so probably therefore I don't see this notebook. So therefore I go to my directory here, Pavel Den, which was created, okay? And so whatever name you provide, you can provide any name for your directory, okay? I've provided name Pavel Den. This is my first name and 3 letters of my last name, okay? And this directory was created. So therefore, I cannot see, I'm not a new user, so therefore I cannot see it as a new user, okay? So then this directory will be created, okay? And in this directory, in the created directory, there will be a new README file. Again, you click it with the right button and click it open with Markdown previewer, okay? And you will have one more README file, which explains actually briefly what type of one-zone nucleosynthesis post-processing calculations you can do with this TINA notebooks. Here it says you can do, you can simulate using one-zone model. iProcess nucleosynthesis that I've just mentioned. This is a neutron capture nucleosynthesis process for intermediate neutron density, like 10 to the 13, 10 to the 15 newtons per cubic centimeter. You can simulate one-zone nova nucleosynthesis, X-ray burst nucleosynthesis. This is nucleosynthesis that occurs on a neutron star accreting hydrogen and helium-rich material. And also one-zone nucleosynthesis simulations for co-collapse supernova, okay? And if you select one of these processes that you are interested in, you should go to the corresponding directory here on the left. I'm going to show you, as an example, one-zone nucleosynthesis post-processing simulations for iProcess. So therefore, I go to the directory here, subdirectory iProcess, all right? And there is also a README file here. Each directory has a README file. So first you go to a README file. Again, you click the right button open with Markdown previewer. And README file in each directory explains what you should do to run these nucleosynthesis simulations. So now I'm in one zone I process nucleosynthesis simulations in TINA. So I'm not going to read now all these sentences. I just summarize what should be done. Okay. So it actually explains here that you can run 3 types of iProcess nucleosynthesis simulations, or 3 cases. They are called weak iProcess, Sakurai's iProcess, and second peak iProcess. And here there are references to publications which actually explain you what these 3 types of iProcess nucleosynthesis mean. Okay. As the first sentence he explains, you are supposed to use 3 notebooks in the corresponding directory. There are each of these directories, iProcess, Nova, X-ray burst, and co-collapse nucleosynthesis. All of them have 3 notebooks, main notebooks, which are called model runner, result explorer, and rate changer. So therefore, when you're in one of these directories, you first read the corresponding README file, then you start these 3 notebooks, you find them here. This is model runner, okay? You double click left button, double click it. So model runner notebook has started. Then you go to rate changer, we can postpone this. So model runner and result explorer. This is result explorer, double click with the left button, okay? Okay, so now let's go to model runner notebook, okay? So it also explains how to run this, to run these models. So actually it says to run the model, just execute .ppn.exe in the following string here, okay? And let me, yeah, you can switch between cases before you run this code. You can switch between cases in the file ppn frame.input. So again, I double click with left button this file, okay? And you can see there are 3 cases here. Again, case 1, second peak, case 2, Sakurai, case 3, weak. So in order to choose one of these cases, you have to uncomment the corresponding 2 lines here. Case 3, for instance, now I choose case 3 for weak iProcess. So to uncomment, you just delete here the exclamation sign, right? And don't forget to put exclamation sign in the case that was open. So here, case 1, and here, case 2. So I'm sure that when you install your directory for the first time, you will have this case 3 weak iProcess uncommented. This is what I've done with my work. So after that, I save the file. Save file. This file is saved, and now I go to model runner, and I'm about to start running the code. As this notebook explains, you should execute command /ppn.exe here. Let me start it. Yeah, execution of Python cells, of course, Shift Enter. Okay, and you are supposed to see something like this. So when calculations actually start, okay, now you can see there are calculations. Okay, this number 5455 is just the time step of integration of the solution of the equations of nuclear kinetics. Okay, so I just scroll this till the end until I see that the calculations are stopped. Okay, they're still going. They're still going. Okay. Okay, the calculations now have stopped, and the calculations have stopped. This circle now is white. While calculations were going, it was black. So calculations stopped. Now I can check in my directory with command ls. So if output files were made. These are output files, ISO underscore mass. These files contained a list of mass fractions of isotopes, stable isotopes, produced in this process nucleosynthesis calculations. Okay, so now I'm going to save this output data files in a directory, save run directory weak I process, I will call it. Okay, shift enter to execute. Yeah, now I check again the directory, my main directory. Sorry. You see now there are no data files, output files in the directory because they were saved in directory with name run underscore weak underscore I process. So when I check content of this directory, run underscore weak underscore I process here, I see that these files are now moved to this directory. Okay, so my calculations are done with model runner notebook. Now I go to notebook results explorer, which allows to do some simple analysis of my computed data files. Okay, so there are instructions here. You can read them later. Execute all cells. Let's execute this cell. The cell just fills Python notebook with right functions, scripts. Okay, done. Now here I have to provide the right directory where my computation results of my computations are run weak I process. Right, this is directory. When I execute this cell, it will read the output data. So it takes some time. You can see this circle is black, meaning that data are being read. Okay, and also there is asterisk here, which means, yeah, now this cell is ready. It's the circle is white. I see there are 512 cycles. We call cycles time steps. So that this means that each output file. So I have 512 output files. So therefore, I can have look in one of these files starting from 1 to 512. So therefore, here I have to provide the right numbers. Let's take the last calculated file with number 512 and make some plots. Okay. It takes some time. Oh, sorry. Yeah, this plot. So this plot shows, as you can see, mass fractions with these colors. So there is a color map here. Decimal logarithm of x. X means mass fraction of isotopes with different neutron number and proton number, right? Okay. So you can see this weak I process produces unstable isotopes away from the value of stability. For instance, proton number 56, this is barium. There is no lot of barium produced. As you can see, its mass fraction is of order 10 to the minus 14, because weak I process produces intermediate mass isotopes. Here you can see this is 50, magic number, by the way, proton number, neutron number, etc. So this notebook here, Result Explorer for I process, it's very simple. So it's just for beginners. If you are interested in analyzing in better, more detailed analysis of the results of I process, one zone I process nucleosynthesis computations, then you should go to this directory, which is called notebooks here, which contains 3 additional notebooks, which allow you to do more detailed analysis of one zone I process computations. Let me start all these notebooks, 3. Double click, left button, double click. Okay. So, for instance, the third notebook, which is called neutron density and exposure, right? Each of these additional notebooks, it allows you first to choose the case that you are interested in. So now we are interested in case weak. This is for weak I process, right? Because when you choose here the case, the notebook will adjust itself so that they make the right plots that look nice, okay, for the corresponding case. Okay, so now we have a weak I process, so therefore let's leave case equal weak. Let's execute cells, shift enter, okay. The first cell, the second cell, third, and so on, okay. The fourth cell, as you can see again, case weak, and run directory, run weak I process. This is where our previously computed data are. So I click this one. Now I read the data. As you can see, again, we have 512 time steps. Now prepare quantities to plot, shift enter. Oh, sorry. Then 1 year is not defined. What it means? 1 year was defined here. Why 1 year is not defined? I didn't execute this. I didn't probably execute this. Okay. Now. Yeah, now it works. So I didn't execute one of the cells. I just missed one of the cells. Okay, so now executed this cell. So now neutron density. Okay, so you can see this cell makes a plot of neutron density as a function of integration time. So this is integration time in seconds, and this is neutron density in neutrons per cubic centimeter. And you can see how neutron density was increasing with time in our computations that we've just done. So it goes to 10 to the 12, and finally it reached close to 10 to the 16 neutrons for the weak process. Okay, what we mean by weak process, you can read about this in provided references. Okay, now neutron exposure. Neutron exposure is the integral of neutron density times neutron thermal velocity time integral. Okay, so this is neutron exposure as a function of time again in seconds. Neutron exposure is usually measured in reversed millibarns. Okay, you can see the maximum neutron exposure reached in our computations was about 1.2 reversed millibars. And finally, neutron exposure, neutron density in one plot. So the same curves, but summarized on one plot. You can see this is neutron exposure on the right axis and neutron density on the left axis. Now let's go to this notebook. Plot charge of nuclides and reaction fluxes for one zone I process calculations. Okay. Or let's go to first elemental abundance distribution comparison with observations. We still have a case weak. Execute this one. Execute this one. So this cell chooses the right setup for cells for the case. We have weak case. What's happened? Name of tills is not defined. I didn't execute this cell. No, I did execute it. Probably not. Yeah, probably not. So all cells should be executed. Now it's okay. Run with process. Read results. Okay. Now make some plots. It takes some time. You can see the circle is black, which means the cell is working. Now you can see we have a plot, decimal logarithm of mass fractions of different isotope of different elements as a function of proton number. Okay, let's go for relative mass fractions. Let's execute this. So. Okay. This is a similar plot, but with respect to initial abundance, mass fraction divided by the initial mass fraction x sub naught. Okay. Now where we are, plus. Okay. Oops. It's not defined. I didn't execute this. So. Hmm. Yeah, yeah. Okay. So this is my working directory. So therefore, this is the wrong reference. This should work. You will not have these problems in your installation because this already worked. I changed something. You can see this work. Scaling by paint. I'm just showing you slides that you can get with this notebooks. So in this plot, we compare results of our computations, this curve, with observed abundances, you can see. So this black dots with error bars, these are observed abundances, okay? And so on. So you can use these additional notebooks to do more detailed analysis of one zone I process nuclear synthesis computations. Okay. Right. The third notebook here, I skipped it because it says that in order to make the plot of reaction rate fluxes, this is a very useful plot, you actually need to do computations with one option included. Let me just show you at the end of our meeting today. If I go back to iProcess, and if I go to PPN frame input file, so in order to make reaction rate flux plots, you will have in PPN frame input file to change this iPlot flux option from 0 to 1. It explains here. 0 means no print fluxes. 1 means print fluxes. So if I now change it from 0 to 1 and repeat my computations in the first notebook, model runner notebook, then computations will be done with reaction rate fluxes in the output. It takes a little bit longer time, not much, a few minutes, but then we can plot reaction rate fluxes in the third additional notebook. So I'm not going to do this right now. Okay, I just tell you about this possibility. And now I'm going to stop my explanation for you how to use these notebooks, and I will just ask you for the questions. So stop sharing. Okay. So guys, that's it for today. And I expect that those of you who already sent me your GitHub IDs, right? You should try during this week to use Tina, okay? Please try to use Tina. And please don't hesitate to ask me any questions, right, that will arise. And don't be sorry, okay? Just ask me any questions and I will, as soon as possible, I will answer your questions. I will help you, okay? So don't hesitate. So your task for this week to get familiar with Tina, okay? With Tina. So I was surprised that I didn't see this first notebook in Tina. Which actually makes your directory. But probably this is because I'm not a new user. So therefore, the first thing when you go to Tina, check if you have this notebook that makes your directory, okay? You should just provide a name of your directory for this notebook, and the notebook will clone all this stuff and make your directory. So this is the first thing that you will have to do, and just let me know if it was successful or not, because I already have the directory. I'm not a new user, so probably I didn't. Therefore, I didn't see this notebook, so I just didn't realize it. Okay, so now just if you have any questions, just ask your questions, and then we will stop.
So I have one. I already made a directory, but it was almost a year ago, and
Yeah.
it's a stupid one. So how do I delete the directory so that I can make a new one?
You can
Or
just
can I
Yeah.
Can I just update the current one?
Yeah, you can try to go to your directory, right?
Uh-huh.
Yeah. Just a second.
I faintly remember that we used to do it through the
Git
through the
pull.
terminal in the notebook.
Yes, of course. I didn't show the terminal, so therefore I think I should start sharing my screen again because I didn't show you that. Okay, now when you in this in Tina, you can say here file, file, new terminal, right? This opens a terminal here, just a Linux terminal. So now you go to your directory. Okay, first let's check ls. We go to network, whatever, network school. I go to my Pavel Den, right? Or, okay, Pavel Den, right here. So this is, I am in my directory. So in principle, I think I can just execute here git pull to updates. Let's check, okay, git pull. Yeah, you can do this probably the same. What's your name? Nihil, right?
Yeah.
Yeah. Okay. We go to Nihil.
Okay. So I'm doing it.
Yeah, you can do this. You can try git pull in your inside your directory.
Yeah, I just did it. I think
Yeah,
it's updated.
It should. Did it update your directory?
Yes. Let me try it again. Yeah, it's already up to date. Yeah, I just did it.
But it reported some updates, right?
Yes.
Because in my case, it says already up to date because I have.
So
okay.
So the first time I do it, it updates the whole directory, and now if I do it again,
it updates the whole directory. Yeah.
Yes. Okay. Awesome. Thank you so much.
Yeah. So you can use either notebooks or you can just, like I showed you with ppn underscore frame input file, you can click on the left margin the file and edit it, and then don't forget to save the file save. Or you can open a terminal window and go directly to your directory and work with the files like if you're on a Linux machine, right? Yeah, of course. This is possible. So the idea behind this network school Python notebooks was that even beginner can start using this codes. Okay, so for instance, starting with the simple notebook that I showed you, which makes just one plot. But because you are more experienced users, you can use additional notebooks, as well as you can change some files. I will explain, of course, in more detail how you can change input files like ppn frame, etc. later, not today, because but by now we have finished with introduction to stellar physics, and starting from next Friday we will talk about using the codes, Mesa code. You can run, even if you are not a NuGrid member, right? You can still run Mesa code, any Mesa code, as well as Nova framework, Mesa code in the Nova framework. You can run it. You can run it on public and outreach server. Okay, I will show you next time. Okay, so today we've just started. I've just showed you briefly how to start using Tina computational tools. So this week you will try to work with them, and if you have any questions. In the meantime, yeah, just ask them. Yeah, Tajpreet has a question. Yeah, Tajpreet.
Yeah, thank you. Yep, I want to ask for this calculations that you were showing, like for different I process to calculate the yields of different I process nucleides. So this is for some specific mass stars, or we are not going to change the mass of the progenitor star, or we will also change the mass of the initial star? Like, what is the mass of the star in which these directions are happening?
I see your question. So the answer is, remember, in one of README files that I showed, there are 3 references for the 3 I process cases.
Yeah, I remember.
Yeah, so you just go to those references and have a look at them. These are published papers. So they explain what we mean by weak I process, by second peak I process, and by Sakurai's object I process. Okay.
Okay, so yeah, I'll check it out.
So these are just two representative cases of iProcess in three types of environments. Okay, yeah, you just have a look at the references. Okay.
Yeah, okay, I'll check it out.
Okay.
Thank you.
Okay, if there are no more questions, that I'm going to stop recording, and bye bye everyone.
Thank you.
Bye
Bye-bye.
bye.
Bye bye.